Morning, everyone. Good afternoon or good evening, wherever you are in the world. My name is Malak Bachri, and on behalf of my research collaborators at Southern Arkansas University, I am honored to present our work, Persistent Homology and Segmented Thinking Model for Zero-Shot Medical Image Segmentation. It is a novel hybrid model that fuses topological data analysis with deep learning to achieve fully automated segmentation in X-ray images. Let's face the challenges. Knee implant segmentation is a critical task in orthopedic diagnostics, yet it's far from being straightforward. X-ray images often suffer from overlapping bones, soft tissue interference, metallic artifacts, and varying contrast conditions. These factors introduce ambiguity in shape and boundary recognition that necessitates advanced segmentation techniques to improve outcomes, making manual annotation labor-intensive and traditional models brittle to unseen data. Moreover, most current segmentation approaches rely on annotated datasets or handcrafted features, which limit their scalability and consistency across clinical settings. So, to overcome these challenges, we introduced PHSAM. It is a zero-shot, fully automated segmentation pipeline that unites persistent homology. It's a mathematical technique that, from topological data analysis, that analyzes the birth and death of topological features across different scales of data and extracts in multi-scale structures. And the segmented big model, or like we call it SAM, it's developed by Meta, which is a large vision model trained on 1.1 billion segmentation masks across 11 million images. So by fusing these two, PH-SAM automatically identifies segments implants even in previously unseen X-rays without requiring any user prompts or retraining. So unlike traditional models, PHSAM offers the following advantages. It does not require annotated training data, thanks to its topology-driven unsupervised detection. It is capable of zero-shot generalization enabled by SAM's massive pre-training. It reduces annotation costs and user efforts by eliminating human-in-the-loop segmentation. And lastly, it offers robustness across different imaging conditions, implant types, and contrast levels. That makes it highly adaptable for both clinical and industrial applications. How does it work? It's very simple. The PHSAM model proceeds through the following stages. So for the input, it takes a knee X-ray image and it converts it to grayscale and pre-processes it. Persistent homology constructs a filtration process defined in the equation right there, based on grayscale intensities and extracts persistence diagrams, identifying topological features like connected components and voids that persist across scales. These features are then used to derive regions of interest, acting as automated prompts. The image and these prompts are then fed into the SAM architecture. It basically starts with the image encoder, which is powered by an MIA, multi-autoencoder pre-trained vision transformer, minimally adapted to process high-resolution inputs in fast regional convolutional networks to extract rich global and local features from the input image. These features represent the image's visual structure and are essential for subsequent segmentation. And then the prompt encoder, which typically uses user inputs such as points, boxes, or text to guide the segmentation process in SAM. But now we can automatically identify critical areas in the image that might represent an implant, a tumor, or any abnormality guided by pH-derived signals. So lastly, aided by the prompt encoder, the mask decoder refines the segmentation output, gives you the top, the bottom, and the full implant, ensuring high accuracy by utilizing the fused topological and visual information from both pH and SAM's vision transformer, as we can see in this output right here. We explored three feature fusion techniques: concatenation, element-wise addition, and feature weighting against the ground truth segmentation. We found out that the concatenation technique outperformed the rest with a Dice coefficient of 0.89 versus 0.85 and 0.79, respectively. So as per the dataset collection and testing protocol, we curated a dataset of 90 annotated knee x-rays from the Osteoarthritis Initiative, OAI, with the Mayo Clinic knee radiographs, as well as with the guidance from an orthopedic surgeon. Out of 100 randomly selected OAI knee radiographs, 55 images were annotated. 35 in-scene images were also added to assess the generalization capabilities of PHSAM model. Moving to results, PHSAM achieved a composite dial score of 0.80 across the 35 test images, which some scores reaching up to 0.98 on individual samples. This performance was achieved without any fine-tuning on test data, confirming PHSAM's generalization ability and automation. What's critical here is that this level of precision was accomplished entirely without human input. No annotation, no clicks, and no prior domain-specific training. PHSAM is more than a segmentation model. I believe it's a step towards universal medical image understanding. Its design can be extended to CT scans or MRIs. It is also domain flexible, which means it can be applied to industrial quality control, airport security scanning, and any area that requires real-time, high-precision object segmentation. So in conclusion, PHSAM provides a topology-aware zero-shot segmentation hybrid model that automates implant identification with no human input, no retraining, and state-of-the-art performance. Looking ahead, we plan to extend our model to PHSAM2, which will support 2.5D and 3-dimensional segmentation of volumetric datasets such as MRI scans and CT scans. We also plan to benchmark PHSAM against other deep learning models in a unified evaluation framework. I believe that would be all. Thank you, everyone, for your attention. Please refer to our published paper for more details and feel free to ask any questions. I am here to answer them all. Thank you.